Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 6.3, day 2, entitled Trigonometric Functions of Angles. And we're going to talk about the last two objectives today. We're going to review some of our trigonometric identities, and then we're going to talk about a formula to help us find the area of a triangle using the trig identities. And when we're dealing with our trigonometric identities, remember that we know all of this reciprocal information already. We know that cosecant is 1 over sine, secant's 1 over cosine, cotangent's 1 over tangent, or cotangent could be cosine over sine, and tangent could be sine over cosine. Okay, so we've been talking about those reciprocal identities along with our traditional sine, cosine, and tangent trig functions. And then in chapter 5, we also talked about these three Pythagorean identities. And remember, this first Pythagorean identity, the sine squared plus cosine squared equals 1, that's based on the unit circle. X squared plus y squared equals 1, and the equation for a circle, for a unit circle. Okay? And this is why the x value in an ordered pair is sine, so we can substitute the sine in there, and the y value for a terminal point on the unit circle is cosine. Oops, I said that backwards. Well, it works the same way. X in the ordered pair is cosine. Here we go, cosine squared. And then the y is our sine squared, but it still equals 1. Okay? So it's the same as that. It's just in a slightly different order there. Now, if you remember, in order to get these other two Pythagorean identities, we took this original sine squared plus cosine squared equals 1, and we divided everything by sine and by cosine. So if we divide that whole expression by sine, we end up getting this. Okay, sine divided by sine is 1. Cosine over sine is cotangent. 1 over sine is cosecant. Okay? And if we take that original trig or Pythagorean identity and we divide everything by cosine, we'll end up getting this trig function or trig identity. So we'll have the sine over cosine, which is tangent. Cosine over cosine is 1, and then 1 over cosine is the secant. Okay, so they're going to have you do some more problems with those types of trig functions. And this is good exercise for what we're going to be doing later on in the chapter as well. So this we haven't really seen too much of yet. So this is definitely something you want to practice. This is new stuff. In part A, they want you to express sine in terms of cosine. So the only trig identity that we had, or the Pythagorean identity that we had the sine and the cosine in it, was the sine squared theta plus the cosine squared theta equals 1. Now when they say to express sine in terms of cosine, that means they want you to solve for sine, basically. So if I was going to solve this equation for sine, I would subtract the cosine squared over. And right now it's still squared, so I have to take the square root of both sides. So then I will have sine of theta equals the square root of 1 minus cosine squared theta. Now remember, you can't take the square root of 1 and get 1, and you can't take the square root of cosine squared and get cosine, because they're being subtracted. Addition and subtraction are like handcuffs. You can't just undo them with another operation. Multiplication, that's a different story, okay? Multiplication, you can break the terms apart, but not when you're dealing with addition and subtraction. And there's one other thing we need. Remember, when you're solving an equation and you are taking the square root as a step in solving it, then you need plus or minus in front of your answer. Now remember, sine can be positive in some quadrants and negative in others. So depending on what quadrant we're in, we could have a positive value or a negative value for that sign. So again, that's important as to why we need that positive and negative in front of our answer there. Okay. Now part B, this one's a little more challenging, a little more thought-provoking. It says express tangent in terms of sine. Now, we didn't really have a trig function or Pythagorean identity that had tangent and sine in it. We have a tangent and a secant, okay, but we want tangent and sine. We do have this right here. Tangent is sine over cosine. So that's what we're going to work with, okay? So we need to remember that tangent is equal to sine over cosine. And we're dealing with the second quadrant. All students take calculus. So as we get to our final answer, we want to remember that in the second quadrant, only sine is going to be positive. So any sine in our answer will be positive. Any cosine is going to be negative. Okay? Now, we have tangent, and it's sort of expressed in terms of sine already, but we only have sine in the numerator. We got to get rid of this cosine in the denominator. Okay? And somehow we've got to change that cosine into a sine. Well, the Pythagorean identity that we have to do that is right here. Sine squared plus cosine squared equals 1. Except this time, instead of solving it for sine, I'm going to solve it for cosine. Okay? So I will take my sine squared theta and my cosine squared theta, set it equal to 1, and then I'm going to solve it for cosine. So I will have cosine squared theta equals 1 minus sine squared theta, and then I will take the square root of both sides. So I'll have cosine squared theta equals plus or minus the square root of 1 minus sine squared theta. So I'm just rewriting it and putting it in terms of cosine. So now I will have tangent of theta is going to be sine of theta over, now instead of cosine, I'm going to write this, 1 minus sine squared theta, and it's all going to be the square root. But now cosine in the second quadrant is going to be negative. So I need the negative value there. Because technically my denominator is still cosine. I've just solved it so that it's in terms of sine. Okay? So I know sine is positive in the second quadrant, but really this is for tangent as well. So tangent needs to be negative too. So if I put a negative here, that's going to make that whole expression negative, which still follows the rules for signage in quadrant 2. Okay, so these types of problems are going to be a little more tricky, a little more thought-provoking, but really it's just reworking those trigonometric identities and the inverses and the Pythagorean identities and combining them and using them to write different expressions. Okay, last thing we're going to talk about is how we can find the area of a triangle. Now traditionally, area of a triangle is base times height divided by 2, or 1/2 times base times height. Okay? And when we're dealing with certain shapes of triangles, we may or may not know the height. Okay? But we can always drop in a height. We can always make a height. And we can make it an altitude so that it's a right triangle. And then we can combine a little bit of trigonometry in here as well. Okay? Now, we're using a right triangle aspect in order to solve or find the area of a non-right triangle. So this big right triangle that we have here is not a right triangle the way it is now. So we're going to drop in that height and that altitude to make a right triangle inside the non-right triangle. And then we can use some rules that we know in order to make an equation that's a little bit more user-friendly. Okay? So if we were actually going to find the height, if we were going to do 1/2 times base times height, I know my base of this triangle, the base is going to be A. Okay? So that's my base. So I'm still going to have 1/2. The base now has been replaced with the A. The height of my angle, if I'm going to find that, I've got to do my opposite over my hypotenuse. I can't do opposite over adjacent because this A is for the whole length of the bottom base of the triangle. I don't want that much. I only need a little part of it. Okay? So that dimension I don't know. Unless they tell me this base of this other side here, the left side of the altitude, then I could subtract. I could have A minus something for the right side of the altitude here. But I don't know that. So I'm going to do opposite over hypotenuse, which is sine. Remember, sine is opposite over hypotenuse. Okay. So then I have sine of theta is going to be h over b. So if I solve that for h, then I'll have b times the sine of theta. Okay, so that's my height, and that's what they've substituted in there, b times the sine of theta. Okay, so that's my formula that I'm going to use then so that I can find the area of the triangle. And there are other applications that you can do as well. If you know an internal angle and not an external angle, you can, remember, you can drop in that altitude or that height wherever you need to. So if you can't put it on the inside of the triangle, you can drop it down outside the triangle as well. So that's what this slide is reminding you of. Okay? And then this distance across the bottom here, that forms a straight line. So then you take this internal angle subtracted from 180, and then you get this outside angle. Okay? And then you could still do opposite over hypotenuse for this angle. You could still do h over b. Okay? So here's our equation then that we're going to be using. 1/2 times a times b times the sine of theta. And a and b are going to be our two side lengths. And then sine of theta, that will be our angle in the triangle as well. Okay, so here we have A and B and C. We have our triangle ABC, capital A, capital B, capital C. Okay. Remember that the little lowercase letters are across from the capital letters. So this side is opposite angle A, so that's little a. This side here technically is across from little from angle C, so it's little c. And then this side here, this B, this would be little b over here. Okay. Now the formula said you have to take 1/2 times a times b times sine of theta, but really it's just 1/2 times the side times the side times the sine of the angle. Okay? So don't get too hung up on, oh my gosh, they didn't give me b, they gave me c instead. Don't get hung up on that. It's basically just substitution. We're going to plug in those two sides and that angle. So we're going to do 1/2 times 3 times 10 times the sine of 120. Now this is in degrees, so you're going to need your calculator in degree mode. Okay? And again, when you simplify this, 3 times 10 is 30, divided by 2 is 15. So do 15 times the sine of 120. Okay, put that number that you're multiplying the sine by out front, or do the sine of 120 first, get a number, then multiply it by 10, then multiply it by 3, then multiply it by a half. Okay? Don't do this multiplication, the 10 and the 3 and the half, don't do that after you type in the 120, because if you don't put the 120 in parentheses, then your calculator is going to take 120 times 10 times 3 times a half, then take the sign of that huge product that you got. And that's not what we want to do. So when you put that into your calculator, you should get 12.99. And it's going to be area, so it's centimeters squared for our units. And if you're asked to write that in a complete sentence on a quiz or a test, hopefully you could do that. You could say the area of the triangle, or the area of triangle ABC is 12.99 centimeters squared. Okay, so that formula is a good application of how you can use trigonometry to help you when you don't have a traditional triangle that works with 1/2 times the base times the height. Okay, we don't have a height here, but we can use trigonometry to help us figure out the height. And now we have a formula to find the area of a non-right triangle using trigonometry. Okay, so these are your problems for tonight so that you can practice these concepts. Again, the important ones to practice are all the ones that deal with the Pythagorean identities and the inverse trig functions. Okay, so make sure you have those concepts down. The area ones, that's just pretty much basic substitution. Remember, all the odds are in the back of the book, and the evens are worked out in the binder in the classroom. And if you have any questions, come on in and see me before school.